Good morning, everyone. This is Mr. Couple. This lesson is for my IB Physics SL Year 1 class, and I'm going to be teaching you about the equation of state for an ideal gas. If you haven't completed the investigating an ideal gas lesson from the beginning of this week, please make sure that you've completed that before you watch this video. There's going to be some concepts that you're going to need to explore and understand and learn before I want you to do this video. Okay, let's get started. So first up, we're going to talk about three main ideas today. So the first is we're going to talk about what is pressure, how does pressure make sense for a gas. The second thing we'll be talking about is the mole concept, that the Avogadro's constant. You probably remember that from chemistry. And then the third idea is we'll be deriving the equation of state for an ideal gas from the investigations that we did in those experiments, and then using it to solve a few problems. First up, we're going to talk about pressure. So I want you to consider this box, and inside this box, this closed box, there's a bunch of gas particles, and they're like bouncing all over the place, moving around. And so what I want to do is I want to list what are all of the quantities that are associated with the state of this gas. And when we say state, we mean like the physical properties of this system. So we want to make a list of all of the properties, all the characteristics, all the quantities that we can measure that describe the physical condition of this gas. All right, so some obvious ones would be temperature. So I'll list that down there. So temperature. And remember that when we're measuring the temperature, what we're actually measuring is the molecular kinetic energy. Let me start my timer. The second thing that we can measure about the gas would be the volume, like the space that it takes up. So, in this case, it would be the dimensions of this box. So we'd have this width, this height, and then this depth, and we just multiply those together to find the volume. What are some other things we can think about for this gas? And the other ones aren't so obvious, but it turns out that the number of particles matters, or we could say like the mass / number of particles. And the last one that we can talk about would be, we would be talking about the pressure of the gas. So under how much pressure is this gas? And these quantities, these are the conditions that establish the state that the gas is in. And you can see that they're related to each other. Like, and we did in the experiment, we found that, if we increased or decreased the volume, that would have an effect on the pressure. So a lot of these quantities are connected to each other and they're related very intimately to each other. And so that's the goal of this lesson, is that we want to create an equation that links all of these quantities together. One thing to notice is that we've got the molecular kinetic energy, but where's the potential energy? So where is the interparticle potential energy? And the answer is that there isn't any. And the reason is because it's a gas. So when we have a gas, we say that the interparticle forces are basically zero. The particles are so spread out and moving randomly that they're not actually ever interacting with each other beyond when they collide. But we say that when they collide, they experience elastic collisions, so there's really no loss of energy due to these collisions. So we could pretty much just ignore the interparticle forces when we get to talking about gases. Now, obviously, this is not true, but what we're going to say is that these are called ideal gases. And so the ideal gases, we make a few assumptions about them and stuff like that. We'll be talking more about the assumptions that we make that allows a real gas, to be thought of as an ideal gas. We'll be talking about those in the next lesson. That'll be next week. I want to first define what is pressure. So we talked about this idea that pressure matters up here, but what is it? What the heck is pressure? Like volume and temperature, that makes sense. Like, volume, like you've known that since you were a little kid. And temperature, we've been talking about that for all of the previous topic 3.1. Well, let's talk about pressure. So what is pressure? So the definition of pressure is it's a measurement of the amount of force that's exerted on a surface per unit area. So this picture is explaining that pretty clearly. So you have this object and it's being pressed into the surface. And then what we're saying is how much force is exerted across this area. So it's like the distribution of force across an area. So if we want to turn this into an equation, if we say pressure is the amount of force per unit area, then we'd say that pressure P, it's a lowercase p. I always mix it up. In IB physics, it's lowercase p, but in most places we use capital P. So lowercase p pressure is equal to the force divided by the area. And the area can be in any unit. Whatever unit for area you use ends up determining what the unit of pressure is going to be. Also, the unit you use for force. I'll talk about that in a second. So, what are the SI units of pressure? So, the SI units of pressure are newtons divided by cubic meter. So, meter cubed. And this unit, a newton per, I don't know why I put cubed. I got volume on my mind. Square meters is area, right? So you've got length times width. So if we've got 5 meters down here and 5 meters over here, the area would be 5 meters times 5 meters. So it would be 25 meters squared. Okay, meter squared. The unit of newton per meter squared, or newtons per square meter, is called the Pascal. And it's named after a famous scientist, and the abbreviation for Pascal is capital P, lowercase a, and the capital P in the abbreviation tells us that it's named after a person. So that's the SI unit of pressure. It's called the Pascal. It's a Newton per square meter. There is a special note that I want to make here before moving on. This is probably not going to matter at all, but I just need to mention it. Pressure is always defined as the vertical component of the force. So if you've got this force exerted on a surface, realize that you can't push a surface if you're the horizontal component, if you're pushing sideways, you're not actually exerting a force on the surface. So the sideways component of this force doesn't exert any pressure. That it's only the perpendicular to the surface that exerts a pressure. I'm trying to erase that arrow. That was gross. Okay, here. So this component is the component that actually exerts the pressure. And so you can see from the right triangle that we've drawn here that that's the cosine. That's the side that's adjacent to that angle that we're measuring to the normal, where the normal is a line that makes a perpendicular to the surface. So pressure is always that green line that I drew there. It's always that perpendicular to the surface. So if you have a force that's being exerted at an angle, the horizontal component, or the component I should say that's parallel to the surface, won't contribute to the pressure. Only the perpendicular one does. So you could say a better definition would be to say F cosine theta over area, but just realize that when I write this formula F over area, I'm assuming that F is already the perpendicular component. So just a special note. We live at the bottom of an ocean of air. I don't know who said that, but I've heard it all the time. This is the truth. So think about right now, like just look around the room that you're in, and think like you have all this air above you going up to the outer atmosphere of the earth, and all that air is like an ocean of air, and that air is pushing down on you. So if you imagine like from the very tippy top of the atmosphere all the way down to where you're standing on the surface of the earth, there's this entire column of air that's pressing and pushing down on you. Like the weight of all that air is pushing on you. So we can ask, what is the pressure that the air exerts on us? Like if we're at the bottom of this ocean of air, how much pressure is there on us? Well, this unit, it's actually a unit of pressure. It's not a Pascal, it's a different unit. It's called the standard atmosphere unit, or the ATM. It's approximately equal to the atmospheric pressure at sea level. And down here I've got the conversion. So 1 atmosphere is about 1.013 times 10 to the 5th Pascal. So that's 101,300 Pascal. So that's the pressure. Like if you hold your hand out, that's how much pressure is being exerted on you from the air around you. And you don't feel this pressure. Like your brain has sort of learned to cancel it out. Like it's just normal. It's there all the time. So you just ignore it. But that's actually 100,000 pascals of pressure that's on you. So you imagine that if you had a box that was 1 meter by 1 meter, and all the air was pushing down on that box, there would be 101,300 newtons of force pushing down from the atmosphere onto that box. And there's a lot of really cool demonstrations you can do. I'm not going to do it because this isn't really the scope of this class, but you could heat up a soda can and like flip it over and put it in some cold water, and the can will just get crushed by all that pressure. So that pressure is around us. It's pretty significant. If you put it into a different unit called PSI, that's the American unit. It stands for pounds per square inch. So that means that if you imagine like an inch by 1 inch by 1 inch section of your skin, like 1 inch by 1 inch, then across that area, joop, 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 the atmosphere is exerting 14.7 pounds of force on your skin. Like if you think about a 1 inch by 1 inch by 1 inch area of your skin, the atmosphere is pushing on your skin 14.7 pounds per square inch of your skin. So this is not a negligible force. It's actually really noticeable in specific situations, and I just thought you guys should be aware of it. So realize two things from this. Number one, the atmosphere exerts a noticeable pressure on us. Our brains have learned to cancel it out and not notice it. And number two, pascals are tiny. The unit of a pascal is actually quite small. So it's very likely that you'll calculate answers where you get like millions of pascals or even billions of pascals. It's completely normal to get that. Remember that standard pressure, the standard atmosphere that we feel is 100,000 pascals. So getting numbers of big, high pascals is pretty normal. All right, let's do a calculation-based problem. The picture shows a cylindrical mass at rest on a flat surface. Here's our available data. The height of the cylinder is 0.45 meters. And the volume of the cylinder, so the whole entire cylinder, takes up a space of 0.10 cubic meters. And then the mass of the cylinder is 120 kilograms. So I couldn't really think of like a realistic object that would be like this. So imagine it's like I don't know, like a person who's like modeled as a cylinder. Well, anyway, what we want to do is we want to calculate the pressure that the cylinder exerts on the surface. So realize that this mass of the cylinder is going to be, there will be a gravitational force. It's going to be exerting, pushing down onto this surface here. And so we want to calculate, well, what is the pressure that this object is exerting on that surface? All right, so the first thing we know is that pressure is force per area. We know what the force is because the force is just going to be the weight of the cylinder because the earth is what's pulling the cylinder down, and that's why the cylinder is pressing into the surface. So we know that's just going to be mg. Then what's the area? What do we put for the area? Well, it didn't tell us the area. It told us the height and it told us the volume. So we've got the volume and we've got the height, but how do you find the area from that? Well, you guys should know that the volume of something, and especially a cylinder, is the area of its base times the height of the cylinder. So if we look at that, we'll realize that we were given the volume. We have the volume and we have the height. So the area is simply the volume divided by the height. So the area is volume divided by height. So I can plug that over here, that it's the volume divided by the height. So I can, since the height was on the bottom, I can just move it up to the top. So we get that the pressure of this cylinder, the pressure is mgh divided by the volume. And I want to make sure that I'm showing that this is a volume, so maybe I'll use like a serif to show that it's a capital V. So now we just have to plug in all of our numbers. So the mass was 120, gravity is 9.81, and the height was 0.45, and then the volume was 0.10. Okay, if we plug this all in, man, I notice how crooked it is. I need to try to write straighter. It's difficult. All right, so let me go grab a calculator. I don't have the fancy on-screen calculator, so just bear with me. I think if I try to load it right now, it might slow down my computer, so I'm just going to leave it closed. So 120 times 9.81 times 0.45, and then that divided by 0.1. So that gives us a pressure of 5,300 pascals. Okay, so there we go. So yep, it's pretty typical to get answers in pascals that are in the thousands. Like you're expecting really, really large numbers. So this is like roughly, I don't know, it's probably not a human because a human wouldn't be 0.45 meters tall, but this is a 120 kilogram object. It's fairly tall. It's like half a meter tall, pretty heavy. It's exerting 5,000 pascals of pressure on the ground. The important part though is that takeaway we got there was that for a cylinder, the pressure is mgh divided by the volume. That was an interesting equation to remember and keep in mind. All right, well let's. We usually don't look at like cylinders on the surface when we talk about pressure. We really want to talk about the pressure of a gas in a closed container. So how does the pressure of a gas relate to this? Like, what's going on? Like, how could force over an area be significant if we're wanting to study a gas? Like, what's the relevance here? And so realize that the gas is in the walls of the container, so that this container has these walls. And now what's going to happen is those particles are going to go bonk, bonk, bonk. They're going to smack into the wall, and every time a particle smacks into the wall, it exerts a force on the wall. So you say that like the gas as a whole doesn't appear to move, but remember that the gas is actually made of like, you know, trillions of these little tiny particles flying all over the place. And the pressure of gas is actually those particles pushing against the surface. So if you've ever like, blown up a balloon and like pushed against the balloon, you're feeling those gas particles pushing, bumping out against you. And the important thing to realize here is that pressure is a scalar, because you'll notice that these collision forces, they're pointing in all directions equally. This is only a two-dimensional cross-section of what I imagine is a three-dimensional container. But realize that the forces are pointing in all directions. So to say like what direction does the pressure point wouldn't make any sense. So pressure has to be a scalar quantity. It doesn't have a direction because its direction is really all directions. So the pressure is pushing out equally in all directions. So remember that the pressure is these microscopic collisions that macroscopically manifest as the pressure that we experience. So it's kind of like how temperature is this microscopic idea of like the kinetic energy of molecules. And then, but we experience at a large scale, we experience that as like the temperature, like the feeling of warmth or cold. It's like that with pressure. Pressure is a result of these microscopic collisions, but we feel it as this pressure, as this force that the gases experience, but really it's these collisions that's causing the pressure. Let's answer a few questions about this. So here are two identical samples of gas in a closed container. The only difference is that one is at a higher temperature and the other is at a lower temperature. So the question is, which gas is under a higher pressure? If pressure is collisions, well, we know that in the higher temperature, the particles are going to be moving faster. So we'd imagine that when a fast particle smacks into a wall, I'm trying to draw a fast particle, it looks really stupid. So if I've got a particle that's moving very quickly, shoom, 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 and it smacks into the wall, it's going to exert a much larger force on that wall than a particle that was going slow, that was like barely moving at all. And so the second thing also is that not only will there be a greater force because they're hitting the wall with more force, but also because the particles are moving more quickly, there's going to be a greater number of collisions with the wall. And so all things tell us here that if you have a higher temperature, you're going to have a higher pressure. And so it's going to be that one. And just think of that from the microscopic perspective of these particles moving around. It makes sense. If the particles are moving more quickly, you're going to have stronger and more frequent collisions with the walls of the container, giving you a greater pressure. Let's look at this one. The picture shows two different states of a gas. We got state 1 and state 2. This is the same gas, but what's the difference is that in state 1, there's just fewer gas particles. In state 2, there's greater gas particles. But as you look at the arrows there, the gas particles are just randomly moving. It doesn't look like there's any higher temperature in one than the other. Like it looks like the average speed that these guys are moving at, the average kinetic energy is about the same. So it looks like the temperature is about constant. So in this case, they both have the same temperature. But what we notice is that the number of particles in number 1, the number of particles is less than the number of particles in situation 2. So how does the number of particles affect the pressure, the collisions? We can imagine like if I just looked at this wall and I said, all right, I'm going to track how many collisions there are. You could sit there and be like bump, 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 bump. But if we looked at the second container and I detected how many collisions were, it'd be like bump, 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 bump. So there's many more collisions per second. When there's a greater number of particles, you have more collisions per second. So how will this affect the pressure? Well, if we have a greater number of particles, then we suspect that increasing the number of particles would cause the pressure to also increase. The more particles you have, the more pressure there'll be, since there'll be more frequent collisions with the surface. And since the collisions are what's creating the pressure, a greater amount of collisions will give you a greater pressure. All of this stuff makes pretty common sense. You just have to think about it like from this microscopic perspective of these particles moving around. Okay, let's talk about the amount of gas. So that was our one of the fourth quantities we talked about, like the mass of the gas, like how much gas there was. It's going to be important for understanding the state that a gas is in. So we've established that the state of a gas depends on the amount of gas in the sample. As we just talked about it up here. It's like if you have more particles, you have more pressure. But the question is, how do we measure the amount of gas? Like how do you say there's this much gas in this container? I mean, would I say like there's 5 kilograms of gas? That seems kind of weird. Or would I say there's 5 trillion molecules of gas? And it turns out that it's you actually do want to give the number of particles. That's how we do it. So we actually say the number of particles. But you'll almost never like if you go to the store and like buy a can of helium, no one's going to talk about that. But you can see like on this can here, it lists the mass. So it gives us well, they made a mistake there, but they're giving us the kilograms and calling it the weight. But we'll forgive them since apparently this can of gas isn't going to be going to any other planet. So I guess we just assume that the gravity is 9.81. That's fine. So the question is, how much gas is in the container? So if we look at this picture, how much gas is in this container? Well, I mean, it seems like there's 25 kilograms of helium, but it doesn't really make any sense to me. Like, how much is that? Like, how many particles is that, or what does that look like? It's kind of hard to really know. Like 25 kilograms of helium. I mean, helium is gas. Like that's really light. 25 kilograms seems like a lot. I mean, there's probably a ton of particles in there. And so it turns out that, yeah, you could actually calculate out how many there are. So let's calculate the number of helium atoms in 25 and a 25 kilogram sample of helium. Okay, so the way this works is that there's this standard convention that scientists use. It's mainly in chemists, is they use this thing called the periodic table, and it lists that number right there, which is called the molar mass. I think I might be calling that the wrong thing, but essentially what this is telling you is it's saying that helium has 4.0026 grams per mole. So if you have a mole of helium, it'll be 4 grams. So the fact that we have 25 kilograms means we have a lot of helium. And so remember the way this works is that 1 mole of a gas is 6.02 times 10 to the 23rd molecules. That's Avogadro's constant. If you don't remember exactly how that works, I'll show you later. I thought it'd be fun to kind of like work out this problem and then go into explaining it. Okay, so I want to figure out what's the number of helium atoms in 25 kilograms? So the first thing to do is realize that, okay, so I've got 25 kilograms. I got 25,000 grams. I'm going to divide that by that number over there. So 4.0026 grams per mole. And so if I do that, the grams will cancel out and I'll just get per mole, which means I'm just going to get moles. So what I've done here is I've figured out how many moles there are. So I'm going to take 25,000 and I'm going to divide that by 4.0026. And I get 6,246. 6,246 moles. Okay, now I'm not done yet because I know that each mole has this many molecules. So now I just have to multiply those two numbers together. So the number of helium atoms is going to be N is going to equal to those two numbers added up. So 6,246 moles times, I don't need parentheses there, times 6.02 times 10 to the 23rd per molecules per mole. And then I get that the number is just these two multiplied together. So I'm going to take that 6,225 or 245 or 246. I'm going to multiply it by 6.02 times 10 to the 23rd, the Avogadro's constant, and I get this number, 3.76 times 10 to the 27 atoms or molecules. That is a really, 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 really large number. So in this container right here, if this container indeed carries 25 kilograms of helium, there's 3.76 times 10 to the 27 atoms. 3.76 times 10 to the 27 atoms. That is a giant number. I mean, what is that? Like 10 to the 12 is a trillion. So 10 to the 24 is a trillion trillion. We're still 1,000 less than that. So this is 1,000 trillion trillion. That's a huge number. Atoms are tiny, and plus they're packed into that container. This is under high pressure. It's compressed helium, so they're all squished in there. So I just want to quickly review what is a mole if you guys don't remember. A mole is just a number. That's all it is. 6.02 times 10 to the 23rd. It's kind of like saying a dozen. Like if I say, oh, I got 2 dozen donuts. Well, then you know that's 24 donuts. Well, if a chemist says I have a mole, then you know they're talking about 6.02 times 10 to the 23rd of that thing. Here's what a mole looks like. If you have 1 mole of aluminum, copper, carbon, just the coin is there for scale. But you can see that it's that many, 6.02 times 10 to the 23rd. That's just the number. And it just turns out that aluminum has the same number of atoms. 26.98 grams of aluminum has the same number of atoms as 63.55 grams of copper. Copper is just more dense, like it has a higher density, so it takes up less space. So a mole is just a number, guys. That's all it is. So I'm going to give you a little bit more specificity than that. The mole was actually, we give credit to Amadeo Avogadro for figuring this out. The mole is given the unit symbol MOL when you write it out, MOL. It's a measure of the amount of substance that something has. That's all. It's one of the 7 SI base units, along with meters, kilograms, seconds. It's defined as this. It's the amount of substance having the same number of particles as there are neutral atoms and 12 grams of carbon-12. But, that's just the specific definition. It doesn't really matter too much that you know that. 1 mole of a gas contains 6.02 times 10 to the 23rd atoms or molecules. And so that's Avogadro's constant. This is how much a mole contains. So this is the shortcut or the shorthand way of saying what is that? It's not a trillion, but it's like 100 billion trillion atoms. You can just say, it's a mole. So it just gives you like a shortcut way of saying it. So like instead of saying 12, you can say a dozen. Instead of saying 600 billion trillion, you just say a mole. This is how we changed from number of moles to number of particles. So that's all we do. It's just this number allows you to change from moles to particles, just from getting the true number to getting the mole number. So here's a question. How many molecules are in 12 moles of a gas? So if you want to figure out how many molecules there are, you just take 12 moles times 6.02 times 10 to the 23rd per mole. And you can see that this is why it's defined as per mole. It's so that when you multiply it by moles, it cancels out, and then you just have a number that doesn't have a unit. So 6.02 times 10 to the 23rd times 12 is 7.22 times 10 to the 24. And there's no units on this because it's just a number, and you don't put a unit on things that you're counting. That is a 24. So 7 trillion. The human body consists of roughly 1.2 times 10 to the 27 molecules. How many moles is this? So now this is sort of backwards because we've already got the raw number here. So if we want to figure out how many moles it is, we're going to have to take 1.2 times 10 to the 27 and then divide it by 6.02 times 10 to the 23rd per mole. And so that way you get per mole, which is just a mole. All right, so that's going to give me 1.2 times 10 to the 27 divided by 6.02 times 10 to the 23rd, and I get 1,993 moles. So we can say that a human has about 2,000 moles of particles inside you. So that's the whole idea, is like, what's easier to say, 1.2 times 10 to the 27 molecules, or say about 2,000 moles of molecules? It's much easier to say moles, and that's all the moles does. It just lets us take what would have been big numbers and express them as much smaller, simpler numbers. Okay, so let's talk back to the simulation. How much time do I have here? I feel like I'm drastically running out of time. Yeah, I am running out of time. So here's the question. This is, if you didn't finish the experiment, this is where you're going to start to get confused. So you should have had 4 findings. I'm just going to look at 3 of them. You should have had that pressure is inverse to volume. You should have had that volume is direct to temperature, and pressure is direct to temperature. These are called the gas laws. So we call these the gas laws. You could write these another way. So like for this first one, you could say that this says that P times V is equal to constant. And this equation says that V divided by T is equal to constant. And this equation says that pressure divided by temperature is equal to constant. So these three laws are the gas laws. And what we want is to combine them into one equation. And if you do that, you'll get what's called the equation of state for an ideal gas. So first we want to see, well, what does it look like these guys have in common? So let's see. So I can see that I have PV here and then another V here. It looks like the over T is always on the bottom. So if you play around with this, you can see that what you end up getting is it's PV over T. That's equal to constant. And that's what happens if you combine all of those guys together, is you end up with this relationship that the pressure times the volume divided by the temperature, that'll always end up giving you a constant number. So no matter how you change the pressure, the volume, and the temperature, no matter how you change it and mix it up and do all these things to it, you will always find that pressure times volume divided by temperature will always give you the same number. Okay, it turns out that this constant value right here actually has another thing in it that was constant. So for this experiment, remember we always made sure that the 500 was never changed. We always kept the 500 the same. So that meant that there's actually an additional variable in there that was also constant, and that was n times constant. And that n right there is the number of moles. So we'll just use number of moles. I mean, we could have put any number there. We could have put, you could have even put a mass. You could have put a kilograms in there. You could have put whatever, but the number of particles, the amount of particles was constant. We're just going to use moles because that's the convention that we've decided to use. But it could have been anything that you stuck there. That's my time. I'm not done. All right, I'm going to finish this up and then I'll just end it. So I'm almost done. So the last thing is that this constant thing right here ends up getting a name. We call it the gas constant. And the symbol we use is R. So we just experimentally measure this. So it's 8.31 joules per Kelvin per mole. It's just the gas constant. That's all. It turns out that like if you do this experiment and you measure all this stuff, you get this number, 8.31 joules per Kelvin per mole. So if we rewrite this equation, which is the way that it's always written, this equation is written as PV equals NR, there's our constant, times T, where we just take that T down there and just multiply it over to the other side. And then this equation right here is called the equation of state for an ideal gas. So I'm going to leave the lesson here. I'll ask you a couple of questions about this. I'm not going to do these worked examples. I don't have time, so we'll have to do those in a future lesson. That's fine. All right, have a great day, everybody. I'll see you later.